this afternoon for coming. It's a great privilege to be here at the Alan Turing Institute, and thank you very much for the Alan Turing Institute for hosting this launch event. This is the first special collection of papers the Society, or the Royal Society of Open Science, has published. It's a very interesting and novel thing for us to be doing. I thought I'd give you a very brief overview today of what I do, what the Royal Society does, what Royal Society Open Science does, for those perhaps who don't know. So, Royal Society Open Science is the newest of the research journals published by the Royal Society, launched in 2014. We publish across the range of the sciences, and it's just one of the things that the Royal Society does. The Royal Society publishes journals, works at public engagement, raising public interest in science, and also does a lot of policy work. In fact, one of my colleagues, Susanna Riddell, is with us this afternoon at the policy section, and I'm also with my colleague Alice Power, who works with me on the journal today. So between us, do feel free to ask questions after the talks this afternoon. We'll be glad to answer them for you. So, Royal Society Open Science is our newest journal. It covers all the sciences, mathematics, physics, biology, computational stuff. You name it, we do it. The journal's innovative in a number of ways. We offer open peer review for those authors and referees who would be interested in doing that. We operate an objective peer review model, so only papers. We don't make judgments on the impact or interest level of manuscripts that are submitted to the journal. We only assess the quality of the science. We are, as I say, open access, so free at the point of use for readers. We mandate open data. So if you're submitting a paper to us, we insist that as an author you give your data and underlying digital materials to the journal so that other users can mine those resources and use it for their own research. We also have an international editorial board which comprises many representatives from around the planet, including fellows of the Royal Society, but we're always keen to expand our diversity, and we're looking actively at ways of doing that with the editorial board. So if you do have suggestions about that, please come and see me afterwards. We'd be delighted to have a conversation about that. We have a number of benefits for authors and readers of the journal. Firstly, and perhaps most importantly, we have no charges anywhere. If you submit to us, you're not charged. If you read us, you're not charged. There are no page charges, no colour charges. Free at the point of use, however you define that. We have a CC BY, beg your pardon, attribution license, which means your papers are widely disseminated across readerships. So no page limits, so authors can explain and expand their work to whatever degree they like. We're quite happy with that. All papers submitted to the journal, if they're published, are press released by the Royal Society's press team, which has led to wide national and international media coverage of many of the papers that we publish, including a number, in fact, of the City Analytics collection today. And although we don't make active judgments about the quality, well, the impact rather, of papers submitted to the journal, we are interested in seeing how widely they are shared and interacted with by the wider public, and we look at article level metrics with that. So lastly, before I hand over to our speakers, if you want to find out more, this is our website address, which you can also find in the flyers and so on at the back of the room to the right. You can email Alice or myself at this address. We'll be happy to get back to you. You can submit research if you have any at our login portal here. And as I say, Alice and I, and indeed Susanna for that matter, are happy to answer any questions later on. Two last quick things. At the back of the room, I think most of you have already seen, we have a number of flyers and handouts that you can take away at your leisure, including some hard copies of the journal, well, the papers in the collection. As there aren't enough of those, unfortunately, to go around today, due to the overwhelming interest, if you are interested in getting a copy of those, if you want to write your name and email address perhaps on the whiteboard at the back of the room this afternoon, I'll make sure that we get some copies to you later on. But thank you very much. I shall pass over to our first speaker.
All right, let's see if this works. All right. Okay, very good. Thank you very much for the kind invitation, for having me here today, and hello everyone. Again, my name is Luca Iello. I work at Nokia Labs in Cambridge, here in UK, and I'm a member of the Social Dynamics team together with Daniele and Miriam. We do research work in the general area of computational social science with special focus on cities and urban informatics. Myself, my training is in computer science, and I've done a bit of work in network science. But recently, since 2 or 3 years, I've done some work in the area of urban informatics, and I slowly discovered that many pieces of work in these areas find their main motivation in this trend is called urbanization. So basically urbanization is this phenomenon for which many people increasingly more people are living in cities or moving to cities, and this trend is basically unstoppable. It cannot be stopped. It is foreseen that by 2050, more than 70% of the population in the world will live in densely populated urban environment, and this, of course, calls for smart and efficient technologies, policies, techniques to cope with this trend. Right? Now, the answer to this problem, so the way in which some people are dealing with this problem is try to optimize efficiency of things that we are doing in cities. And this is basically the smart city movement, the smart city agenda, right? So all the research done in smart cities tries to optimize, for instance, the efficiency of the way in which we manage our transportation systems in cities, or the energy management and storage, or even the way in which we deal with the security of our streets through CCTV cameras, for instance. So now, all these things are very good for a city, and they're necessary for a city to scale to a certain size, of course. But the point we want to make here is that these are not the elements, the crucial elements that make the life of a city great, the life of a city happy for people who live in a city, right? In fact, if you look back at all the literature in social psychology, urban planning, and I'm thinking about the work done by Camille Lynch, Stanley Milgram, and Jane Jacobs, for instance, all this piece of work from different angles, they point out that the crucial point to guarantee a happy life for people living in cities is not really maximizing efficiency, but has to do with the psychological perceptions of people in urban environments. So if we can understand and measure reliably how people perceive psychologically their own streets, while they stand on a street, where they go around, we can then enable technologies or even enable interventions in the urban space that can change these psychological perceptions for good, right? And so improve in the end the quality of life in a city. So the tricky part here is that psychological perceptions are by definition quite tricky to measure because they're intangible, are in the domain of the intangible, okay? So the very big problem here is how do we reliably measure at scale these perceptions? So 3 years ago now, together with Rossano, who is a professor at the University of Torino, who is here in the audience today, and with Daniele, we embarked on this journey, on this quest that we like to call the quest for a good city life, that basically aims exactly at doing this, measuring what is usually considered not measurable, these intangible properties of people that go around the city and what they sense, what they think, and so on. Okay? So now in 2014 we started by measuring one first concept, that is the concept of beauty. So how beautiful a urban space is. Okay? So, of course, you can say beauty is a very fuzzy concept, very subjective in a sense, but there are ways to measure it in a way. So, for instance, by comparing things. So, human beings are very good at comparing pictures, for instance. And so, usually when one person shows these two pictures to an audience, to a group of people, and ask them which one is the most beautiful or the most quiet or calm and relaxing, usually there is a big consensus that the picture B is probably better than picture A, all right? So if you ask enough people, you reach a consensus, you can sort of estimate the perceived collective beauty of a place. Now, leveraging this small trick, Daniele, back in the days, started this crowdsourced initiative that it was called urbangems.org, and it's just an online game, very simple, where people are shown two geolocated pictures from Google Street View of London, and they were asked which one is the most beautiful according to your own judgment, okay? So the trick here is that if you collect enough pairwise comparisons for the set of photos that you show, what you can do is to rank the pictures from the most beautiful to the least beautiful. So all of a sudden, this concept of beauty that was very fuzzy to grasp at the beginning is measured because you have ranked photos by collective beauty, okay? Of course, it's an average, but it gives a pretty accurate indication. So now the problem with this approach, so this is nice because you can look at the elements and the picture at the top, at the bottom, and do some inferences. The problem was the scalability, right? So with this approach, you need a crowdsourcing experiment for every photo, every picture in every city. And so we wanted to scale this up to global scale, to planetary scale. And the answer to do that was social media. In social media, we have a lot of data that is geolocated, uploaded by millions and millions of people spread around the world. In the case of Flickr, for instance, or Instagram, you have pictures, so visual data, geolocation, of course, and also textual data, for instance, in forms of comments or tags. And these are literally billions and billions of pictures all around the world, right? So the intuition is if we could have an initial ground truth of labels, beautiful or non-beautiful, attached to these pictures, we could use the features, the visual and textual features of these pictures to train a classifier, to train a model. And this is what we did. So given an initial training set of pictures tagged as beautiful scenarios, beautiful urban sceneries, and non-beautiful ones or ugly ones, if you like, what you can do is to train a model where a machine learns which are the visual cues or the textual elements that are associated to beautiful picture or non-beautiful pictures, right? And so for any new picture that comes in, the machine can look at the features of the picture and decide whether it is a beautiful scenario or not, right? So doing this sort of learning, you can generalize the approach and run it at scale. The first application we proposed was a very simple one, but quite effective. It's called EpiMaps, and stems from the observation that most routing tools that you have on your phone, they recommend just the shortest route, right? So from A to B. And we want to do something better, a little bit better. So here you have a map with several points. All these points are pictures from Flickr or Instagram, for instance. The red one correspond to ugly places as classified by our method, and the green one are good places, nice places. So if you have the point A to point B, the shortest route could pass through a nasty area. We don't want that because we don't want to maximize efficiency, but we want to maximize the experience. And so the algorithm, what it does is to recommend a slightly longer drive, but still quite short, that maximizes the beauty of the things around you while you walk. All right? So we run some experiments and user studies about this in the city of Boston and London. Here, for instance, this is one of the maps we've shown from a starting point to a destination point in Boston. The blue one is the shortest one. The red one is the recommended one, the most beautiful one. And respondents to these surveys, which were around 50 people, assessed that indeed the recommended paths were more beautiful than the shortest one and not much longer. So the cost, the additional cost, was really worth the walk in the extra minutes, right? So it was very good, very nice, and we were very happy, all right? However, there was a problem with this, and all the respondents, many of the respondents of our surveys noticed that there was something missing. So basically here we were focusing only on the visual aspect of a street. However, as human beings, we have several different senses, not just sight, right? For instance, think about smell and sound. So we might choose to go through a street because of the good smell of a bakery, or we might want to avoid it because of bad smell of trash. The same thing goes for sound, right? So nice, vibrant music in the street or voices could be nice to hear, or mechanical sounds and cars might be not really so pleasant, right? So we optimize our choices based on all our senses. And if you think about it, it makes sense because there is a wide spectrum of smells and sound we can hear and decide upon. The problem is that if you think about it, city councils usually are focusing on a very tiny spectrum of smell and sound, which are the bad smells and the noise. And so this is because basically these aspects, the bad smells and the noise levels, are estimated and measured through complaints. So people complain about people shouting in the street, and this is recorded, and so you have data for that, right? But of course, this is a very narrow perspective on the smellscape and the soundscape of a city. So this is the most of the data that we have because measuring smell and sound is difficult and even expensive, right? So measuring the exact smell in a street, like with nasal ranger, or the exact type of sound in a street, there are several different initiatives and projects that try to do that at scale, is expensive because you have to place sensors everywhere, right? And try to estimate this for every street segment. It's not really scalable. So what we wanted to do is to, again, to scale this approach to planetary scale, and we focus on both smell and sound. In this particular talk, I'm going to focus on sound only, because this is the topic that is contained in this paper, published in the Royal Society, that is called the Chatty Maps, and you can have a look at it. So, to begin with, so what we did is we took a step back and went back to the literature of people studying sound in open environment, in urban environment. And specifically, there is this book, The Soundscape from Schaffer, that describes and categorizes sounds that can be heard in the city, for instance. Okay? So there are some keywords and categories attached to these keywords. So we wanted to build a representative set of words describing sources of not only noise, but different sounds. And so we parsed this book, we collected some words, but these words weren't too many, and so we wanted to have a bigger coverage. And so we went to this open source of data. This is called Free Sound. It's a portal. It is open. People can go there and upload sounds they record in cities with also geo coordinates, right? And they can tag these sounds, these audio files, with tags that are user generated. Okay. So what we did is we extracted all the tags from Free Sound to have a larger set of tags, and we verified that these tags indeed were a superset of Schaffer's one. Okay? Then, given this unstructured collection of tags, we wanted to structure them in categories, like Schaffer did, right? So through that, we did a little bit of trick. So we collected all the Flickr pictures that contain these sound tags, okay? And then we looked at co-occurrences of sound tags in the same picture. For instance, if you have two words, noise-related words or sound-related words, scream and shout, and you have 50 pictures that contain both of the words, you have a representation like this. So 50 times these words co-occur in the same picture. And you can replicate the same game for all the pictures that you have and build a graph of co-occurrences, okay? What it turns out, this graph of co-occurrences has a very clear, what is called community structure. So there are some communities that are tightly interconnected, but not very well connected with the rest of the graph, right? So here, for instance, we have all the tags that are about music, here about mechanical sounds, there about people and human sounds, and so on. So there are automated techniques in graph analysis, graph theory, that are called community detection algorithms, that are able to automatically detect these dense areas in these graphs and therefore extract the dense communities and extract these sort of topics, in a sense, okay? So the final outcome of this was this categorization. That is a hierarchical categorization of sounds, which is represented in this abstract wheel, where at the center you have the main 6 top-level categories of sound. There are human, nature, music, mechanical sounds, noise related to transportation, so like railroads, and indoor-related sounds, like office, church, and so on. Then you have second-level categories. For instance, inside human, you can have people walking around, or the voice of people, and so on. And then some examples of words, for a total of about 300 words. The very surprising and nice thing was that this categorization resembled quite strikingly the one that Schaffer provided in his book. So the data-driven approach was exactly the same and the theory-driven approach, which was very nice. So given this thing, we could go back to social media and do our job. So basically here is an example of a Flickr picture in which you have a lot of metadata and the picture. This is clearly a picture depicting people playing music. You have a geolocation, here is in New Orleans. You have tags that match our dictionary, our vocabulary of sound tags, and you also have some time. So you could in principle build a profile over time of sounds in the city. And the result is what we call chatty maps. And basically for all the cities in which you have enough coverage in social media, you can build a profile of each street segment, so very fine-grained, of the sound profile of a street. In this case, could be, for instance, 75% of transportation sounds, 20% human, 5% music, all right? And this is done by taking all the pictures within this bounding box around a street segment. So this basically the work was done. We could profile the sound of a city. Now, some of you may think, well, this is not really very convincing because you're just matching words, right? So who tells me that this really corresponds to actual sounds, right? Because social media data is very noisy, so you don't really know. So what we needed is some checks with orthogonal sources of data. And we did that with two cities, data set from two cities, Barcelona and London. So the first thing that comes to mind, of course, I have this data about sounds. I put them on a map, and I mapped them, right? So this is, for instance, London. All the traffic-related sounds, you map them, and more or less you see that these occur along the main streets, which sort of makes sense. It gives a first indication this makes sense. You can do the same for all the other tags, nature tags, so water flowing, birds chirping, and so on. And you see that this is along the river or in big parks, which makes sense. So mapping the first thing says, all right, so we are in the right direction. We can do something more quantitative rather than qualitative, and for instance, look at the correlation between the presence of a certain sound as recorded by social media and the type of street as recorded by open tools like OpenStreetMap. For instance, in a primary street, so it's a big street with cars, there is a strong positive correlation with transportation sounds and a strong negative correlation with nature sounds, which makes a lot of sense. If you take a different type of street, like tracks, like footways in the countryside, you have a strong off-the-chart correlation with nature and negative correlation with all the rest. You have either nature or silence. Okay? So this already adds something about this sort of validation. And then you can further validate that using yet another orthogonal source of data, which are noise levels that are measured by city councils through sensors, and there are models that can propagate this sensor data through all the street segments, and so you can do a correlation at street segment level. And what you can see is that you have a positive correlation between the noise level and traffic sound, and a negative correlation between noise level and nature sound, which again makes sense, right? So there are several of these checks in the paper, so these are all built to verify that actually we are measuring what we want to measure. So to conclude, in the last couple of minutes, I just wanted to discuss something that goes even beyond the senses. So I talked at the very beginning about psychological perceptions, and we want to tie the sensorial perceptions, smell, sound, sight, with what happens in our brains, right? In terms of emotions, for instance. So there are several emotion models. This one is one of them. It's an 8-dimensional emotion model that is called the Plutchik wheel. And basically it has dimensions like joy, trust, disgust, anger, and so on. And each of these categories are mapped into words that one could look up on social media. And so we can see how the social media words related to joy correlate with different sounds, for instance. And what we can see is that, for instance, traffic-related sounds are negatively correlated with joy, for instance, and positively correlated with anger and fear, which makes a lot of sense. For music, music sounds are correlated with joy and sadness, or if you want melancholy in a sense, the mixture of the two, and negatively correlated with anger and fear. So this is basically the first door to open on the emotion spectrum of people. The last thing is about even more sophisticated models of perception that are used for from people who work in sounds, in studying sounds. Here is a chart that is commonly used that describes how a sound is perceived along two axes of pleasantness versus eventfulness. And it defines these 4 quadrants of a sound being chaotic, vibrant, monotonous, or calm. So to map our sounds in this chart, we teamed up with Francesco Letta, who at the time was a researcher at, I think, Brighton University, Sheffield, it was Sheffield, sorry. And so what he did is to conduct what he called the sound walks. In the sound walks, people went around, I'm finishing in a minute, people went around and annotated the sounds they were hearing and the perception of these sounds. So as a result of this, you can have a matrix that maps the conditional probability of a sound, for instance, being calm, given that is a sound of nature. So there is a high conditional probability of a calm sound being from nature and a low probability of a chaotic sound being from nature. So basically here you have a tool to map all the sounds into human perceptions. So at the end of the story, what we can do with all these things is to build a layered model where you have different senses, emotions, perceptions, and build the maps out of that. This is the project we call Good City Life. There is a website. Go there and play with it with several maps of different cities. You can have this representation. So Rossano built all of them. You can have an exploration of us at street segment level and look at the composition of sounds and smells in different cities. So we're very happy that in the past we had a lot of attention from the press. This doesn't really speak to the quality of the research itself, but it says that people can relate to this type of research, right? And the reason why this is true, the reason why we think this is true, is that, again, we are putting people at the center and not efficiency at the center, which is, I think, is very important. All right, thank you for the patience and for listening.
So we have around 5 minutes of questions, and if you just raise your hand, and I'll bring you the mic.
I like this very much. It gets to one of the applications that I think you're on the verge of, really. If you're in your own town and you're walking home late at night, you know which areas aren't safe or which are going to cause you anxiety or worse things can happen. This looks like a great way of doing that when I'm visiting a city or my family is visiting a city, that we could have sort of what were perceived as safe spaces because there was a reasonable number of people, there was low anxiety, there was queues that were, you know, as opposed to other parts of the city that you might walk into which are perhaps perceived as spaces that would make people anxious and possibly at some risk. So I wonder if you've thought about producing an application like that or trying to mock something up. I think it would be really popular on people's, phones.
That's a great observation, and indeed it's to the point. Safety and especially perception of safety is something crucial in all these applications you mentioned. And in this layered approach, you can imagine an additional layer for safety perception, right? We're actually trying to work in measuring how people perceive the safety of a city compared to the actual safety of the area, which can be quite different at times, and also to plan intervention. So the very big unsolved thing here is to close the loop with the public, right? So to have either interventions or applications that can really help people to live their life in cities in a better way. And this is exactly a very nice example that you did about one possibility of doing that, of course.
I've got a research group that have looked at pollution in London, and they've used as a primary source not only London city air from King's College, but also UCL carbon black. And what they've done is they've looked at the correlations, particularly between noise, where there's a strong correlation, particularly with traffic noise and nitrate pollution and so on. But they've also looked at, obviously, meteorological data like wind speed. So I'm just wondering whether an extension of this might be also air pollution.
Yeah, indeed. So in the piece of work I didn't present about smell, we exactly used the data source you mentioned to correlate those NO2 levels with our smell tags in London. And it turns out that the correlation is very, very high there. So basically, yes, you can use an orthogonal source to verify the approach, and the same would go for sound too. But yeah, definitely. So we've done that, and it's in the paper about, it's called smelly maps, yeah, for a change, yes. Yeah. Sorry.
Did you see anything interesting around differences in perception of beauty? For example, you know, some people might think graffiti or street art is really nice versus traditional art. Did you see anything in your research in beauty or the other areas? Yeah,
that's an excellent question. So I think that there are two elements here. One is the cultural aspect, so different cultures can perceive things differently, like graffiti perceived differently for different cultures, or even personalization, right? So different individuals can prefer different routes, for instance. We didn't look into any of these two in the context of cities, so some colleagues of ours looked at differences in perception of beauty, for instance, in pictures across cultures. We haven't done that for cities, we might do it in the future. And of course, if you want to ship an application that does this, for instance, the mapping, the happy mapping, personalization is key, of course. So, yeah.
Thank you, that's very interesting. I'm interested in, have you looked at all at doing engineering with this data? In other words, you know, for instance, you talked about finding paths between a place A and another place. In terms of modifying the paths that people can take or engineering the urban environment such as to plug gaps, because some of these, I noticed just on the example you showed, there were some areas it went through which probably weren't as nice as other areas, actually creating coherent routes. Have you looked at that?
No, that's an excellent observation, and I think that's the next step, right? So basically, the engineering of routes that you were mentioning is basically the derives I was talking about, right? So you have the shortest route, and you modify this route in a better way to have a better experience. Or you can do the same with other sources of data, like you were mentioning. So that's exactly the part that is facing applications that we need to look at to have an impact on the general public, which is exactly what we need to do. Yeah.
Just to take this further in, brain-computer interface hardware is coming down in price now. Did you think about that? Because I think that that's kind of the next obvious deeper thing in from this.
Yeah, so excellent, good point, very good point. So I personally think that the phones that we have, these devices, the smart devices, are completely not the best solution to navigate our urban environment, right? So when we want to experience the city, we want to look up at things, not to look in our phone. Experiencing with new types of interface, it's crucial to bring these sort of knowledge and augmented experiences to the public. So the one you mentioned could be one. I'm not sure it's going to be the best one to deal with these sort of problems, but yes, it's definitely one area to explore because it's the way to bridge the gap to the population. So doing these things just on the phone, it will be nice, but it won't be enough. That's my impression.
Okay, let's say a big thank you to Luca Aiello.
Thank you, guys.
Well, thank you very much for having me in this event. So I'm a physicist from CASA, and I collaborate with architects, geographers, urban planners, mathematicians, and so forth. So this, what I'm going to present here is a result of an effort from everybody from many different perspectives, and try to basically understand how in this multidisciplinary effort, in order to understand the urban patterns and universal patterns that exist everywhere, how can we extract from disciplines such as biology and other disciplines tools that can serve us to look at this in a more generic way. So in this sense, this work started from the inspiration of the brain. So basically, while looking at a biological system such as the brain, you can see that it is intrinsically hierarchical. And this hierarchy emerges from the fact that there are modules in the brain that need to be interconnected very, very closely. So they're really the result of different modules having higher functionalities that need to be interconnected between them. So in a way, is it what we create as human beings, being part of this system, the result of something intrinsical in this way? So when one looks at the brain, we observe that you can try to poke into this hierarchy of systems by putting thresholds into the stimulus of the brain. So you stimulate the brain, and then some different parts of the brain are going to light up. So here what you have is a threshold of the stimulus. You have the threshold of the stimulus given in terms of a probability number, and then you have different modules lighting up in the brain and then end up being interconnected, okay? So this gives you a sense of a hierarchy. In addition, this can be described in terms of percolation theory. So people in physics know how to do this and then are able to unpack these different hierarchies of how the different modules interconnect and what does it mean. So in this sense, looking back at the urban system, the question is, what would be the corresponding threshold of a stimulus in an urban system in order to have these different hierarchies, right? So that will be, of course, the interaction between the individuals, okay? So what we have created in terms of our street network and our urban systems is the outcome of this need to interact be able to trade and so forth. So in this sense, what I'm going to take as the main system in which we're going to explore whether there are any of these patterns is a road network, okay? So the motivation is that what we have created as a road network nowadays is a result of this interaction. So it all started in communities needing to trade and needed to interact one by one. And then, of course, now you will argue these interactions are no longer physical interactions, but they take place in the cyberspace, okay? So the whole idea here is to say, okay, even though we live in this cyberspace as well, we're embedded in the physical space. So have we left any traces of this evolution in terms of how we create our urban structures from the interactions? Can we reveal anything, any patterns from these very old structures such as road networks? So if you think in terms of percolation theory, the whole idea is that this connectivity in the space relates to asking the question whether trade is going to take place more closely between entities that are closer in space to each other, whether a disease is how a disease is going to spread in the space according to the intensity of the disease, the way it spreads, and the connectivity of the space. So in a way, our intersection points, our street, represents each of these trees that are burning, okay? So the whole idea then here is to look at each of the intersection roads as one of the trees, okay? So the question is, how will these messages be propagated in space? And the way they're going to be propagated is the outcome of a historical evolution of how we have created the road networks. And how are we going to do that? So the way we're going to do that is to cluster these intersection points according to just proximity in terms of distance. So here, I'm going to take the road network, I'm going to remove the street from the road network, and I'm just going to leave the intersection points. And I'm going to argue that the intensity, the density of these intersection points is what primarily tells you about the intensity of the connectivity of the people when these settlements were forming, which gives rise to the structure that you see nowadays in urban systems. So what is it that we obtain? So when you run this sort of simulation of clustering according to proximity, you will see that all of a sudden there are little clusters that start to emerge until the whole thing is covered up. Okay, maybe this goes too quickly. So here you can see, you manage to see cities, you manage to see regions, and then until the whole country is the one largest connected component that is covering the space. What you see here in colors is just the 10 largest clusters. So here are the colors ranked according to their size. So how can we unpick whatever is happening in this, in this experiment here of trying to reveal the hierarchies in the system? So of course, you use the well-known method of following the largest connected component in your space according to percolation theory, and then you can see that there are many transitions, okay? So there are continuous phase transitions in the space that tell you that something is happening. What does it mean? It means that in these transitions, you have different processes that emerge. So here you have cities that emerge, then you have differentiated regions and so forth, until the whole thing connects into one specific thing. So if we look closely at these transitions, then we observe that the first transition tells you when the cities emerge, okay? So for the ones that are well versed into identifying your cities, you can see that these are not entirely here. This is the core of the cities, okay? But you can see that there is some primarily structure emerging here. All the gray bits, now there are not cities there, they're just not the largest ones, okay? Another of the transitions that can be observed is this one. So this was quite an unexpected transition. So you have to remember here, we don't have a street networks. We only have the intersection of the points. We're clustering just according to proximity. We're not considering anything else. And what you observe is a division here, okay? A division in terms of England and England and Wales. And for the ones that are well versed as well with respect to the division of economic wealth in the UK, you can identify that this division here corresponds very nicely with what you know as the north-south divide, okay? So if we recap at this point, you see that the division of wealth captured according to income per capita at the level of the geographical unit of a world relates very nicely with the clustering of infrastructural points. Okay? So somehow you can argue that there was a differentiation in which the intensity of the infrastructure was developed in one place with respect to another one. Okay? Another of the interesting divisions that one finds in here is this one here, which is, of course, Scotland being a different country with respect to the rest. So, of course, Scotland was a different country many hundreds of years ago, and you can still see a signature in your space in the way the infrastructure was developed of how was it in the past. Okay? And more importantly to consider, of course, while you're having all these sort of clusters emerging, you will expect natural barriers, you know, like parks. At some point in another one, you have Snowdonia here, for example, and so forth. So the natural barriers, of course, are going to give rise to different settlements, to an identification from the urban cores, from the whole patterns of the urban system. But here, you don't necessarily have a range of mountains creating a barrier between Scotland and the rest, okay? What you have just is a signature of the division in terms of how this infrastructure has developed. But then, of course, you will argue, okay, you were considering just the proximity of the points in your space without taking into account all the natural frontiers. So how to take into account the mountains? How do you take into account the rivers? How do you take into account, of course, all these natural accidents that are going to create different settlements here and there? So the way to do that is to take the real road network, okay, which of course is not fully connected, and this is why you would expect maybe a different result from the one that I presented here. So by taking the real road network, the distances between intersection points is going to be the real distance that a person has to travel in the road in order to get from one point to another. So if there is a mountain, you have to go up the mountain and down the mountain, not through the tunnel, whether this is possible or not. So we did this experiment, and what we obtain in this set of maps, you will see that this map looks very, very similar to the previous one that I presented, okay? So the thing is that the UK is quite flat, so there aren't many natural accidents with respect to rivers, big rivers dividing big zones and so forth. So the result is very similar to the things that you presented there when you look at the pictures here. If you wanted to look closely at these results, and hence to look at how it behaves in terms of its mathematical description, you would also see that both have the same behavior. Of course, the difference here is where these phase transitions happens, okay? Whether they happen at a distance of 120 meters or whether they happen at a distance of 300 meters and so forth. So the difference in the distances is the thing that's not universal, but the behavior is very similar. So after we do this exercise, then we're able to construct a hierarchical tree. So this hierarchical tree, you can look at it from the bottom up, in which how you have all the cities of the southeast or the northwest or whatever, in whichever configuration you were to see it, or how you can decompose the whole of Britain into different clusters from which you will have this hierarchical structure emerging. And so coming back to the initial bit of the talk, you will remember that all this is based just on the infrastructure, okay? All this is a hypothesis of saying the hierarchical structure of the urban system that you will know as South Wales, South East, Scotland, East Anglia, and so forth, this kind of structure, you can see it in terms of administrative units. But what about the people? Now that we're in the cyberspace, we connect, we move, we live in one place, we work in another one. How does this relate to the identity of the people, and whether these regions say anything or not with respect to communities living in the different bits of communities living in the different bits of the regions. I think I got it. Okay. So in order to answer that question, we look at the way. So how can you look into the way people feel with respect to their identity? So one way to do that is to look at the way people vote, okay? So what we did is to look at the way people vote in these different levels of hierarchy, okay? So what we did here is you take into account the way people vote and you cluster according to this hierarchical tree, okay? And these are the results that we obtain. So if you wanted to cluster according to your country of birth, so these are the results of the 2010 elections. If you wanted to cluster according to your country of birth, you will have a pattern of this sort, okay? If you wanted to cluster according to your age structure, it will look like that. But if you cluster according to the way to where you belong in this hierarchical tree, it will look more similar to the patterns obtained, okay? So in a way, the physical space is still an important aspect to consider in the way people identify themselves. So even though we can cross in the cyberspace many frontiers, we still attach to this cyberspace and we still interact, to this physical space, and we still interact within this physical space, and we live in one place or another because we feel good or not, and we feel part of this system or not. So I was telling you at the beginning that when you do this exercise, you end up looking at the cores of the cities. But how can you then recover from this hierarchy the structure and the real boundaries of the city? Because this is the next question. Where do you put the boundaries of the city? Where are these cities, right? So I can see the cores, but until which extension? So of course, in this sense, because we're talking about the formological structure of the space, we're not going to consider functional areas, right? So we're not going to consider people or flows because we're in the road the structure, but we're going to consider just the physical extent of the space according to this. So how do we do that? How do we recover this from all this mess of different clusters appearing according to the different thresholds of distance? So of course you will say, and of course coming here from the Alan Turing Institute, you will look, okay, well, we have to look at the statistical properties of all these clusters every time they appear, right? So one of these statistical properties is the fractal dimension. The fractal dimension will argue, okay, but maybe not just the fractal dimension, but the multifractal spectrum, in which you're going to be considered not only the box counting dimension, but also the informational dimension and the correlation dimension. But when are you going to stop this? Well, up to the point that these things here behave in a proper way that can give you a sense of an average, okay? So this, we performed the Shapiro-Wilk test, and we see that this happens until 700 meters. What does it mean? It means that we're not going to consider clusters beyond this threshold here, which makes sense because you can see that here there are no cities any longer, there are regions, but we're going to stop just according to the statistical test and not just by visual inspection. So when we do that, we taking into account that when we're looking at these multifractal measures, what we are trying to get across is whether there is a difference between the monofractal dimension that is more generally associated to cities, okay, in which you do the box counting algorithm, or taking into account the non-uniformity in the way that cities grow, which means when you have a different probability of growth in your fractal at different places, you're going to obtain a multifractal instead of a fractal. So we're just going to see whether there is a difference in the behavior of these things. So when we run this analysis, then this is just the three first, so this is not the full spectrum, it's just the three first multifractal measures, the box counting, the informational one, and the correlation. And we see that by doing this, we obtain some sort of plateau and some sort of maximum that can be identified around 180 meters. If we go to the networks and do the same in order to obtain the fractal dimension, so you will ask me, how do you get the fractal dimensions in the networks? So you do a mass relation of how they grow, so what is the mass of the system with respect to the diameter of the networks, and you compute you compute it, and you obtain the fractal dimension. And in the networks, you also see this maximum. Of course, at a different distance, because here's the percolation on the network that you have to go up the mountain and so forth, or roads that are not straight. So what does it mean? Why is it that my system some sort of maximizes this fractal dimension? What sort of configuration of the space I obtain at this specific threshold? So when you look at it, you see that this threshold corresponds very nicely with what cities are. Okay, so what do you mean by corresponds very nicely? Well, I'm going to get a proxy, which is satellite images, which is the Landsat satellite, the current data set. It has a classification of your space according to what space is urbanized, land uses, what space is green spaces, and so forth. So what you have here on your right-hand side is the red stuff, which is the urbanized space, and then you have all the other green stuff, which is not urbanized. So if I draw boundaries around these ones and I compare them with those ones, well, I don't need to draw the boundaries. I just do a correlation with respect to a grid. I see that the maximum correlation between these two corresponds to the same one at which I obtain my maximal fractal dimension. If I compare the two different analyses, one in the intersection points and another one on the red network, on the road network, I see that I have exactly the same thing. Okay? Which is very interesting, because what we're doing here is saying when you have a system in which you're missing data, you're missing a kind of points of interaction between these things, you can still recover these patterns without having to have the full structure. Okay? Of course, it works here because of the specific topographic configuration of the UK, but it's interesting just to see a first perspective of the hierarchical system when you don't have a full data set in place. So to conclude, we have seen that even though the natural barriers might provide the initial conditions for the formation of settlements and so forth, it is the intensity of connectivity between individuals that have give rise to these road networks that have left a historical dependence on the structure of the urban space. Okay, and by analyzing whatever we have created as a human and cultural society, by looking at just these hierarchical properties using different methodologies from every system, so in this case physics, you're able to recover and have a peek into history of what were these initial settlements. And this is all. Thank you very much.
So again, we have about 5 minutes for questions. I can start with a question. Oh.
So in your last 2 slides, you talk about the results that you find using the intersections only, and using the neural networks basically give you similar results. And this has some implication on dealing with missing data. And I want to understand, like, in what extent this might be useful by having this knowledge.
Yes. Oh, well, I don't need the microphone yet. So basically, OpenStreetMap is a very good platform in order to look at all these structures that we have created so far, right? But OpenStreetMap relies on people clicking and putting maps together according to their knowledge of the space and so forth, and the satellite figures and so forth. But then when you're trying to digitize all this data, you might have things that don't quite construct and quite refer to street network per se, because there are many different types of mistakes. So if you just extract intersection points, you're able to recreate kind of something that will give you a sense of how the structure looks like without having to have all the different bits and pieces. So that's one of the aspects. But mainly, here we're talking about interactions. And when we're talking about interactions, the links between the two nodes are the main bits in which that you're considering a network as your interactions. But can you look at it the other way around, whether you're going to have a higher intensity of these interactions where you have a higher concentration of the nodes that are going to be related to more people. So kind of a question of how can you go around when you don't have a full information of your system.
Sorry to ask another question. Do you have you thought about layer? The distance is kind of similar to time in some ways when you show the evolution. Have you thought about mapping conflicts or historical events with this kind of lens or structure?
Yes. So actually, this work started a while ago, even though it has only been published recently, as some of you might be aware. And we have already done it for the whole of Europe. So when we look at the whole of Europe, we obtain a path in which you will have, of course, Crimea separated from Ukraine because it's a peninsula. So this is a geometrical property. It's not a property that derives from any kind of conflict or whatever. But you would also see that within the connectivity of the space, there were these three different cities that always appear in the news as being problematic, being completely disconnected from the rest of the system at a very early stage. I can show you that later on. And when you look, for example, just at the UK without looking at conflict or things of the sort, if you think about the northern powerhouse and the way that you will think the space needs to be connected, when you just look at the infrastructure, so here, of course, we're not taking into account rail, and then you will argue, well, if you take into account rail, it will look very different. But when you look at the way clusters emerge, you see that Newcastle is just a different cluster. It's not part of the picture, right? And so the question is, if you want to introduce a policy like the powerhouse and so forth, why are you going to incorporate a city that is not naturally connected to the rest of the urban system? And so in this effort, in the European maps that we have, we see as well, for example, Berlin disconnected very early on from the rest of Germany as a separate federal city and so forth. So there are signatures in the space of why the structure that you have nowadays looks like the way it looks.
Thank you. Yeah. Thank you.
Thank you.
So today I'm going to talk about some work that we did with one of the postdocs in my lab, Matt Williams. Matt is now in a AI startup. And today I'm going to give you like a flavor of the type of work that we did in this space of modeling spatio-temporal systems. In particular, with respect to a particular application that is robustness of systems where space and time play a key role. So when I say like a spatio-temporal system, one example is a transportation system. So here you see the London Underground, and then you see the US domestic flights network over time. So in these systems, essentially, nodes are also a physical space, and also when you have a process on them, the process is bounded in a sense by the time it takes, for example, for moving from a certain location in London to another location in London. And essentially, our goal is to try to find a way of merging properties that are properties of the structure and the processes that are happening on them. So in particular, in this talk, I'm going to try to answer this question, which is the impact of failures in a spatio-temporal system. So when I say spatio-temporal system, you might think about generically to many types of spatio-temporal system. One type is the brain network, and also this is quite a nice application, in my opinion, that I think this framework might help in addressing. So the processes in a brain network, you might think about, for example, a transportation network. And failure in a brain network really might lead to disease like dementia. In a transportation network, clearly the problem is related to the fact that you can't move, especially or even worse, when you have emergency, like rerouting people might be a very important concern in this space. Those also try to think about, if you are thinking about like managing London or managing a big city, you need to think about providing resilience in your infrastructure. So this was one of the episodes that usually happen in London, is when I think many people live in London here or work in London. So when essentially the Victoria Tube Station was closed because someone essentially flooded the line with concrete, okay, with wet concrete, and essentially all the Victoria line was blocked for one day, essentially. This is a typical example of the fact that the system itself is quite fragile. Okay, it's quite fragile, and millions of people are using the Victoria line every day. 1 million people for sure. So and then you have essentially these messages that if you are on Twitter, you usually get. So there are severe delays somewhere in the infrastructure. So from this type of experience that we have, we can try to think about how to formalize this problem in a more mathematical way. Okay, and try to think about how we can use the insight from the mathematical models in order to address this concern. So today I'm going to give you like a very brief introduction to the modeling that we did in terms of representation of spatial and temporal properties of these networks. Then I will define the concept of path in these networks, and also try to define some performance metrics for understanding robustness and resilience of this network. And at the end, I will also talk about a bit of random failure and systematic attack for these networks. When I say systematic attack, clearly means that there are some stations, for example, in a metro system that are key, that are extremely important, and the system becomes extremely vulnerable if these stations are hit. So this article was covered by the Evening Standard. The Evening Standard said, okay, you gave some comments in the article. They say you gave very good ideas to attackers. That is true in a sense, but we also raised awareness of the fact that we need to think about how to introduce redundancy in order to cope with these problems. So this is, I think it is also the power of the mathematics here. Okay, so we can really identify the parts of the infrastructure that are the more vulnerable. Okay, so in general, our goal is to try to define a very general framework where we have both nodes that are in space, but they might also move. They might also move because we were thinking about also system where a station is there, but and it doesn't move there in a Pass and Pancras. But we were thinking about also, can we also have a representation where we have users that move, for example? If we want to use this model, for example, for representing interaction, collocation of people moving in the city of London. The same framework. So a very generic mathematical object in a sense. So nodes are spatial, so they are in space, can move. We have evolution over time, so it's a dynamic system, position change, and the interaction between the nodes might not be instantaneous. Clearly, if you are collocated, the interaction is instantaneous. If you have to go from London to Liverpool by train, the interaction is not instantaneous. So this is the idea. So we use a representation. I just give you like a flavor today, but if you are interested, you can read the paper. So this is a presentation of the special collection. So the idea is essentially you can in a classic system like this one, where you can see, when you can see here, you have the nodes, and you have certain connection. And usually, the classic system, you have maybe different changes in the links between the nodes. We want to add something else here. We want to add also some propagation speed in the node. So essentially, over time, so a process takes a certain amount of time for, like for example, a car to go from a node to the other node. Let's say that one node is London, the other one is Brighton. It takes some time to go there. So we have a speed of propagation. If you think a brain network, there is a speed of propagation in the neural network. So there is a delay, okay, a delay. And the delay is important because especially there is a delay to go to from St. Pancras to Paddington, okay? So it's important if you want to study the properties in terms of robustness, not in terms of delay, not only in terms of connectivity, and pure connectivity, okay? So the representation that we use, essentially, we have a network that changes over time, like this one. This is a classic time-varying framework, as this has been widely studied in the past years. The PT is here, they did a lot of work as well in this space. But we have also the idea that nodes can change in terms of location, and also potentially the speed that might change over the links. And the idea is that, for example, you might have, in a road, you might have traffic. This is a typical case. So in a temporal network, you have instantaneous transmission. In a spatio-temporal network, we have a constrained propagation of the link. So let's say in this example where we have, like, for each time slot, you have essentially a progression. So the speed is, the progression is limited by speed. Let's say that is 1 unit per time. You see that you can't complete the entire link in one single unit. So the idea is to try to capture this concept. And so you see here, so you can't reach the nodes. Like, for example, in the second slot, in a classic temporal network, you reach A, B, and D. In this case, you reach only A and B. We want to capture this. How do we capture this? We capture this through a series of matrices. So one is for connectivity, one is from distance, one is for the speed, and one is progress made on the link. Okay, so these are the mathematical, this is the mathematical logic that we are using. And these are, is a matrix, this is a function of time. There are matrices that are function of time. With these 4 matrices, we can essentially model all these possible systems that have these properties. And we are still working on this, but we think that it's quite powerful. And as I said, various applications, including neuroscience and so on. Today, I'm going to talk about just one application that is robustness. So first of all, we need to define path. So path, essentially, we need to define this idea of partial progression. So it's not just the nodes that are visited by essentially, for example, a propagation process, the node that the process goes through, the classic path that we define in the past in time-varying networks or in static networks. But the idea is that you will have also the idea that a time of arrival in a certain node. And in order to define this, you define a spatio-temporal path with the node and also the time of arrival in that node. Okay. So this is the idea. So you have a sequence of visit to the node. This is the start time, and then you have the arrival time. So if you use a representation like that, you can measure latency, you can measure a spatial length, and you can measure clearly the number of hops. That is a classic measure. So you want to have a shortest path that provides the minimum latency and the minimum spatial length. And based on this definition, we are trying to define robustness, that is spatio-temporal robustness. So how do we measure this? So we need to consider 3 dimensions, and we are able to consider these 3 dimensions: topological, temporal, and spatial. And we need to define some measure in terms of vulnerability. So these are the classic measures that you use in temporal networks, essentially. But we need to revisit them in terms of spatio-temporal networks. So we consider temporal efficiency, that is essentially the inverse of the distances between each pair of nodes, but considering the definition of path that I gave, like very informally 2 minutes ago. Okay, I know that the talk is not probably mathematically strong, but I wanted to be quite to reach like a wider audience. So this is the idea, the intuition, and we also consider the efficiency, the robustness. So let's assume that in this, so essentially here you don't consider just the distance, but the inverse of the distance, because if two clusters are disconnected, the distance between two nodes in the two different clusters will be infinite. So you need to consider the inverse. So this is the idea. Why we consider an efficiency, and this is the inverse. And then we consider robustness, considering robustness given a certain percentage of failed nodes. So F is a failure, so like if you have 20% of the failure with respect to an efficiency that is this, that robustness without any failure, we try to calculate what is the robustness, okay? It's a ratio between the case with no failure and the case with certain number of failures, okay? So then we try to calculate the kind of classic measures of robustness in terms, one that is a giant strong component size, that is essentially the size of the largest connected component, classic measure. Then we take a look also at the temporal efficiency, defined just considering temporal networks, but also we consider the spatial efficiency, okay? That is based on the definition that I gave before. Essentially, is a measure of relative change. So if it is 1, you have the same efficiency as an intact network. If it all disconnected, you have 0. And again, relative change. So we consider a certain number of real-world networks. We consider certain metro systems, the underground, the Paris metro, the New York metro, and US domestic flights. We consider also a biological network, the brain of the C. elegans. This is this guy, okay? And so we know a lot about him. The C. elegans, that is essentially one of the toy animal for biology, and a network of communication and contacts between students in Dartmouth that is called the Student Life dataset. All these datasets, by the way, are available on the website on Dryad. Okay. Perfect. So we consider these networks. First of all, we consider random failure, and random failure essentially you select a node randomly, and this node is removed from the network. If you consider random failure, we observe here essentially you have the giant component size here, the temporal robustness there, the spatial robustness there, okay? And this is considered like failure rate. What we observe that the metro systems are extremely vulnerable compared to, for example, a biological system as the brain of the C. elegans. This is quite fascinating because this means that evolution is pretty good, probably, and essentially is a highly optimized system. It's an highly optimized system based on biology. And we see another thing that is quite interesting. The US flights, the network of the US flights is also quite resilient to failure. And this is because, essentially, when you plan a flight network, you try to introduce resilience in your system. And you can, because you can have a new flight. Try to dig a new line in London. So that is the idea. So the fact that it's very difficult to add resilience in a tube network, especially in a city like London, where the tube was not planned. Essentially, there were different companies, competing companies in London. And then essentially you have acquisition and so on. Just after the war, we had some big collection of lines, essentially, they were managed by the same authority. And now we have the TfL. So this is quite important. It's very difficult to add resilience on a system where you have already some lines that were essentially non-planned. In fact, we will see that the characteristic of Paris and New York are slightly different. This is the first message. So then let's consider a bit of systematic attacks. So systematic attacks, we consider two types. We consider the classic types of attacks, like based on centrality and so on. We'll show you later, node degree, in degree. But we also define some new attacks. One is based essentially called path betweenness. That is essentially we target nodes which support many shortest path, spatio-temporal shortest path. And we consider also the betweenness efficiency, that essentially that degrades the temporal efficiency and increase delay in the network. Okay. This is path betweenness centrality, and essentially, as I said, these are essentially the shortest path that go through V between W and U. Okay. And they go through V, normalized through all the shortest path in the network. This quantity essentially represents a node in supporting the connectedness of the network. And then essentially this means that if are essentially the nodes that are at the center of the network, that are connecting, that are represent essentially they are in a lot of shortest path between the nodes of the network. Okay, and quite interesting, you should not consider this map of the tube, that clearly this is a topological representation, but you should consider this map, that is the real map, the geographic map. And you see the colors are the node with the highest value of path betweenness centrality. It's quite interesting. Look, there are some unexpected red dots there. Huh? Okay. We built this map, this spatio-temporal map, using the real-time table. So you know that TFL as it provides like an API. So we download the timetable for one month, and we consider all the possible changes in the service for 1 month. So this is it is the map that we obtain. Then we consider also the efficiency centrality that I said. So essentially, if you deactivate nodes with high betweenness efficiency centrality, you have an impact on the efficiency, on the spatio-temporal efficiency of the network. Some result now. So this is the temporal robustness. And again, as you expect, so essentially here you have several types of attack. The error, the random error, the path betweenness, the temporal centrality ID is the in degree, the out degree, the number of links, the in links and out links, and the betweenness efficiency. Here is quite interesting again. You see the tube, London, Paris, New York City here. What you observe here, you observe that Paris is the most resilient network of the three. And we will see also the characteristics because it has a high redundancy. You can find a station in Paris every half a mile. And is extremely well connected. New York is something in the middle. And here we're talking about targeted attack. If you have a target attack in the US flight, and again, we used a real flights here. So it's not just connection, but we use like a timetable of all the flights in the US. It's extremely redundant. So if you miss your flight, you can go home more or less the same time. Okay, or if they close an airport. C elegance again. Evolution is pretty good. Okay. Okay. So this was Dartmouth. Okay. Now let's see. I want to show you like just a visual representation of what I said. So this is London. As you can see, London. You have a lot of branches that are not so you don't have redundancy at all. So if you close one station here, all the branch is gone. And this is true also for the train network in UK. Yeah? So if you close 2 or 3 stations in UK, you have serious problem. Northern and South are disconnected completely. London, New York City. New York City, you see, you have quite nice redundancy here as well. That probably was introduced a posteriori. But you see the end of the lines, sometimes they connect, except that one on the north in the Bronx. Other lines have sort of nice connection at the end of the line. And that this provides redundancy. This provides redundancy in the network. and see Paris. Paris is a mesh network, more or less. So you can see this also visually. Perfect. So just a summary, because I'm at the end of my talk. I try to present a framework, give like a flavor of the framework that we develop for spatio-temporal networks. This framework allows for avoiding like oversimplification in representation of the network, and we can essentially capture structure and processes at the same time in the same set of matrices. It's quite nice, quite elegant in our opinion. And also I presented some results about resilience to attacks, to failures and attacks of various systems, biological and city systems like metro systems. So going back to my initial example of the random of the closure of the Victoria line, that day when the concrete entered the line, the TfL had to close 6 stations because it's the branch. You know that they closed part of the line. So the two extremities were active. So 6 stations. So if you consider like a random removal, the temporal robustness go to 94% of the ideal case. The case of closing those 6 stations, we have a reduction to 89%. If we target station with the temporal robustness using the betweenness efficiency, centrality, and you close these 6 stations that have the highest betweenness centrality in the network, you have a reduction to 32%. So just 6 stations. And these are also not the usual suspects. So okay, you have Houston, you have Notting Hill, but Reynolds Lane is quite unexpected. But these are the nodes that provide that. Essentially, they are essential to provide like good connectivity also from a temporal and spatial point of view. Okay, this is a takeaway message. Everything is a working distance if you have time. Everything is space and time are really related. And then thanks for your attention. If you have any questions, thanks a lot.
So we have about 5 minutes for questions.
Yes?
I have I have 2 questions. First is, as you mentioned, the network is spatio-temporal, and I can think of space in terms of time as well. In terms of the distance is basically time. So I'm thinking, my first question is, what's the advantage of splitting the two into distinct fields? And my second question is that, is there a scope for automated suggestions of how to increase the robustness of the network in the lowest cost possible?
Yes. So like space and time is very important because you need also to be able to respect some geometric properties in the network. So there is also this aspect, like especially if you are. So we consider distances that are distances like in a metric space. Actually, you might think about also to extend this work to hyperbolic space, like the people did in CAIDA. So, but you can also think in this way. This is the first point. The second point is about how you can automate this. Yeah, it is an interesting problem. It's probably a search problem. I think it's a search problem, but it's an interesting problem. It's an optimization problem. But you might provide, using a system like this, you can maybe to guide the search, using these metrics to guide the search. You can provide some potential candidates to adding resilience here means adding a link, speeding up the communication, the capacity. Because in this system, we don't have capacity, okay? Well, I think you need to increase speed in your link. Yes, but it is a search problem. Yeah. Yes?
How responsive is it to plan B? What I mean is that the first thing you do when something goes down in the network is try and fix that node. If that doesn't work, you have go round it. I speak with experience because Affinity Water managed to lose water to most of Barnet yesterday for 8 hours. So what they do is they come on and they say, we've got all our technicians fixing the reservoir. And that goes on for about 4 hours. And then they say, we've got the engineers fixing the reservoir, and we've got another lot of engineers fixing to bring the water in from an alternative reservoir. It's the same thing applies to the transport networks. It goes down and they try and fix it. Or there's a strike and they try and fix it. But if they don't, then they start running buses.
Yes.
So the vulnerability is the extent you've got a plan B.
Yeah, the plan B here can be really to say users like customers, for example, in a transportation network might have a different route to go on. Like in Hammersmith, you can take two tubes, two lines. So this is a plan B here. You might think also like having like other types of service, like studying this network from like putting like using also the bus network on top of this things that you can do. The plan B usually is to think about, when I say resiliency, is really adding plans B to the network.
Is plan B from the user who knows that they can walk, or is plan B from the provider?
I think the provider doesn't want to upset the customer. So I think
So it's it's to what extent they've got a plan B for the providers.
They should. They should. Okay. Other questions?
Do you have any other questions?
I'm around.
So I just have one more
there is
question.
a question there.
So thank you. I have a question about the map of the betweenness of the stations in London. So you mentioned that you downloaded the timetable from TfL.
Yes.
And how do you compute the betweenness map? Do you use something like the simulation?
Yes. So essentially, it is a search. Yes. So we build a graph, and there is a search in the possibility or exploration of the station. Yes.
Okay.
Yes.
And have you compared the result with the betweenness map from the empirical data, like the real world usage of the tube
you mean in terms of delay, of real delay?
No. So you can produce another betweenness map using the real world data.
Yeah, but these are real world data.
Yeah.
Yes, we use the real world data. When I say based on it is based on real world data. So we use the real world data from the API of the TfL. So it's not a simulation. It is a trace-driven simulation. So we use the data in order to calculate what are all the possible paths.
Okay.
Yes.
Thank you.
Great. Let's say a big thank you to Mirko.
Okay, thanks a lot.
Before I start, I just want to say thank you to someone who isn't here, who is my colleague Des Hyam, who's from the University of Strathclyde. So Des did a great job actually pulling as a guest editor and dealing with our friends from the Royal Society and pulling all this event together and inviting the speakers. And he hates my speaking so much that he's sort of got some infection in his foot, so he's not able to be here today and enjoy this. But truly, Des is getting he's getting into a lot of places, and he's if you get the chance to see him talk, he's very, very good, and he's very, very funny guy. But actually, he's in the vanguard of a movement which is bringing together numerical linear algebra, which we can imagine there's all sorts of things from optimization and sparse matrices and things, with network theory, with evolving network theory of the type Mirko's just talked about, and working in some very applied areas. And so it's been my pleasure to work with him for a number of years. But I'm not going to talk about any of Des's work today. I'm going to do three things. I'm going to talk a little bit about, let's see if this works. I don't know if it's going to work. Should we just take this out? Is it why? If this doesn't come back up, I'm going to give a different talk. Okay, so I'm going to do three things. I'm going to talk a little bit about our paper that's in this journal, where we wanted to attack a question of how we compare actually networks, but in this case they're cities of vastly different sizes. And that has a very practical endpoint, as we'll see. The second thing I want to do is to talk about where some of this is going in mathematics. And the first thing I'm going to do, that's a sort of new topic area for all of us, which is becoming interdisciplinary. But nevertheless, this whole interdisciplinary area is going to drive some new and difficult questions in the mathematical sciences. So I'll talk a little bit about that. And I'm going to start off by doing a bit of mathematics on the grounds that what doesn't kill us makes us stronger, so we can all go away having proved something this afternoon. When you look at cities, they've got a lot of similar infrastructure. We saw the clusters earlier in the talk. They've got a lot of similar infrastructure. They've got police forces, they've got ambulance guys, they've got electricity, power, schools, all of these sorts of things. They've also got people in them. And the network of who knows who really inspired some of this, because we wanted to say, well, are cities really the same? There's been a lot of work on scaling laws, and we'll have a look at those in a minute, just for a bit of fun. But actually, there's a harder question there. If I spend a huge amount of civic money making some intervention in a city, and it's successful, do I then move to the next city and do the same thing? Because it looks the same. It's got the same roads, it's got the same traffic, it's got the same... But is it really, given that there's a social dimension to these things? And I'm going to say that not all cities are the same, actually. That's where we're going with this. But on the assumption that they are pretty similar, this has been going on for a very long time, and Mike Batty and others have looked at the way that different type of things, it doesn't matter, you pick something and then you fit a scaling law to it, and some things scale sublinearly. So as the city grows, if we look across a whole range of city of different sizes, as the city grows, they scale sublinearly, and some things scale superlinearly. And great, so we can measure anything we like in a city, plug it on log paper, put a line through it, and we'll measure the happy.
That will smooth out an awful lot of variation if you log something.
Well, it does, yeah. Happy? Why should there be scaling laws? Why should there be power law scaling laws? Why? Sorry?
Increasing returns, that's where...
Yeah, well, you could have an exponential scaling law. Why don't we see that? Happy? Let's have a look. Let's consider a city as a graph. That's a gross simplification, but if they're going to be scaling laws, it's going to work for graphs. And let's rule out pathological cases. So Q is going to be something I measure. So it might be crime, it might be GDP, it might be whatever it is. Q is going to be something I measure. And it maps really a graph onto a real value R, which is normally positive between consenting adults. Let's let S1 and S2 be graphs on the same set of vertices. So that the edges of S1 are contained in those of S2. So that just means that S2 is like S1 with a few extra edges added. That's all it means. And then let's restrict ourselves to consider Q, where Q of S2 minus Q of S1 is bounded by the relative change in the number of edges. So this rules out some cases. Like now Q can't be, say, the number of distinct components. Because if I just add one edge, I can join two up, and this changes by an integer, but it might be 1 over a million there, or 1 over 10 billion. So this rules out cases like that. it's saying something a bit like continuity. But we can't talk about continuity for graphs because we can't continuously move from one graph to another, except in a limit where the graph is very, very large. But it's something like continuity with respect to the number of edges. We could use this to do some maths if we want, but we're not going to. This just means that if we want to form graphs, we can form up graphs anywhere we like, and we can add and subtract a few edges, and it won't matter very much, considering the measure we're making. So that's reasonable when we're looking at things like production and things like that. If you just add one or two edges in the graph, it shouldn't really make a lot of trouble. Disjoint unions. A union in maths is a nuisance, isn't it? Because if you've got a set ABC and a set CDE, you put them together and you don't count C twice. But in this you do. This is what we've always wanted, isn't it, for unions? We wanted to remember where they came from. So a disjoint union of a set S1 with S2 is really just put the two sets next to each other and then you can relabel them if you like. So they remember where they came from. So you don't... this clearly works for graphs as well if we do the union on vertices. So if I have a graph here and I have another graph here and I just bring them together, that's a new graph. And it doesn't really matter if one vertex here was called the same thing as one vertex here. We'll just forget that and relabel the thing if we need to. Okay? Now, if we have a scaling law for this property Q over all the graphs S, then it really ought to work for a nice subset. And that is if you choose your favourites S, and I'm going to think of that as a ghetto or a community, then little ns denotes the disjoint union of n such communities, particularly n similar communities. We can generalise this later, but stick with me. If there's a scaling law, it really ought to work under these circumstances. And so given a community S, I could imagine a city as being just a disjoint union of a number n of those communities, and then because of the international rules of Q that we've already agreed, I can add a few edges in to join them up if I want, and it isn't going to spoil Q, right? Because we've agreed that Q is sort of continuous with respect to... Okay, so if we've got a scaling law, it ought to work for these. Now suppose there is a scaling function. So this would be like a power law in n or something. A scaling function that describes how the functional Q behaves for the disjoint union of isomorphisms. Then it would have to satisfy this. Q of the disjoint union graph, ns, would have to be this function g of the value of Q just on S and then the number of copies of S I had. That's what a scaling law does. And so we've made no progress at this point. This is all notation. Okay, and now comes the moment, you know, in the lecture where we just do something a bit cute. We try and say, well, what sort of condition does that put on G? Can G be anything? No, it has to satisfy a functional equation. Because if you apply G twice, G of Qn gives me Q of Sn. And then if I apply that with the same thing with M there, then that has to give me G of Qnm. So I just apply G twice. Standard trick. It's very exciting. This is a functional equation. And for those of you with maths and physics backgrounds, you'll know that functional equations always appear at very exciting times in the development of theories, like wavelets, like bifurcations off to chaos, all of those sorts of things. And in fact, functional equations predate differential equations, I'm proud to tell you. So before everybody was fiddling around with calculus and differential equations, this was the game. And it's really interesting today that when we see sort of renormalization type arguments in physics, in mathematics, that we get back to functional equations. So here it is. So I mean, G has no choice but to satisfy this. G of Q of 1 is just Q, because that's just Q of S. So we've got an initial condition, and then we've got to satisfy this condition. And we can guess the solution to that. Here's one solution. Forget this bit on the right there. Q times n to the minus alpha. So that's Q times n to any number I like. So if alpha's negative, it grows like a power law. We've seen the power laws. If alpha's positive, then it will decay. And you can add this extra term on for free. Doesn't give you any problem. Adds an extra constant in. This is one of the general solutions of this equation 3 with its boundary condition there. And you can immediately see that if alpha's positive, then as n goes to infinity, this will tend to a constant beta. So this is just a saturating function which just grows up and is asymptotic to a fixed constant beta. The other alternative is the thing just grows like a power law and goes on. Very satisfactory state of affairs. Are there any other solutions? Sadly, yes, there are. Q to the n is a solution. That's exponential growth. So why don't we see Q to the n when we go over the work of in this area? We don't tend to see this. There's a very good reason. Here's one good reason. It's called the semigroup property. If you fiddle around with this, you sort of want to define n as e to the, I know n is discrete, but don't worry about it. If you define u as log n, and then write h of qu then h satisfies this equation, which says h of q of u, comma v, is just, and this is the semigroup property. So we know how to solve this. We can go and get a solution of any semigroup, and then we can construct a solution for h, and so therefore we can construct a solution for g. Where do semigroups come from? They come from ordinary differential equations. The bottom line of this, it says that if you have a differential equation, then very often you're in the realm of a rest point. And when you're in the realm of a rest point for a differential equation, the growth is exponential, because you've got eigenvalues and things, that the linearized system there, right? And exponential growth corresponds exactly to the solution we've already seen. So one argument is that power laws in observations of functionals on networks are really as ubiquitous as the exponential is in telling us how solutions of ordinary differential equations. We could construct, the sharp-eyed amongst you will see one later, we could construct a functional which had an exponential power law growth. It would have a very peculiar differential equation, but this is the reason we're seeing power laws ubiquitously. And if we see them just on, it's just a property of scaling of networks. Okay, and then if we measure, Q can be pretty much anything which is broadly continuous. Next question, for which Q do power laws exist? Simple solution to that. Actually, if Q satisfies this equation, so S0 is a graph, and then S1 and S2 are other graphs, so we do the discrete union, and when I perturb S0 twice by S1 and S2, then the change in Q is bounded by the difference in the Q's of S1 and S2. This looks like and is a Lipschitz condition. So Lipschitz continuity is a slightly stronger version of continuity than the thing we saw early on. And Lipschitz continuity always occurs in maths when we're looking for existence. And this is good enough. The proof I'm not going to go through, but it's really quite interesting because you kind of prove it by contradiction. You say, well, if a power law doesn't, if scaling law doesn't exist, that must mean there are two graphs which are indistinguishable up to n-1 copies of each of them, and then the nth copies of each of them are distinguishable. And you can pull out a contradiction from that. So in actual fact, this works for a very, very large set of Qs. In particular, if we take any matrix M associated with S, like the Laplacian or the adjacency matrix, then when we put discrete things together, we've got a sort of block diagonal structure. If we take a function of that, well, that's just a function of a matrix. And usually a function of a matrix is just monkeying about with the function of its eigenvalues. And so it turns out that all of those would satisfy this kind of condition, as long as we had reason. So actually, there are, almost anything we can think of in algebra would have a scaling law, and almost all of those scaling laws are like power laws. In fact, you have to work very hard. There's a trivial one where you take the determinant of a matrix. Coming back to structures, so I talked about there a city as decomposable into subcommunities, and that's the nature of this work, which I've done with Tamsin Lee, who's been a postdoc with me for a number of years. So just have a quick look at that. Cities and multiplexes. here is the data. So this data is up on the Royal Society site, and I'll explain what it is. These are reciprocated mentions networks on Twitter. So let's pretend we're doing it for the whole country. So if I at Mirko, and within 4 weeks Mirko ats me, then we've both sent a message, public message, to each other preferentially. We must know each other, really. Or I could say, well, let's do it twice, and twice. So there's some reciprocation. Now, I'm always sending ats to Wayne Rooney, and he's never responded. I've got a lot of advice for Rooney, especially as he's getting a bit older. Needs to drop back a bit. So that's what we've done here. So you only know someone if there's a reciprocated mention over a certain time period. And then we've taken all the geolocated people in these top 10 cities of the United Kingdom. So we saw a lot of these in your networks. You had quite a lot of Liverpool. I'm a lifelong Manchester United supporter, so there's no Liverpool in this talk, nothing for Liverpool. Okay, some of them are quite small. So the Edinburgh is, a few thousand. It's really a tenth of the size of London, which I'm not even showing you here. I'm just going up as far as Manchester. So this is just a sample of these networks. Now, I have produced data for the top 100 cities and towns in the country, and I'm going to make this available to each university can have their own data. I'm having a bit of trouble with that data set at the moment, but when I've done it, because of course we're all getting into smart city territory, and so it's really nice if people can have a view, and especially comparatively, as to where their city sits with others. So we're trying to do that. For the moment, with this paper, we've just worked on these 10 cities, so all of this is there, and there's a nice file where you can pull these reciprocated mentions down and do whatever you like with them. But these cities somehow reflect the social connections within a certain strata of self-appointed Twitter users, and it doesn't really reflect anybody else, okay? So this is not the extent of this, but it's still quite interesting because there are quite large differences in these things, even though, by eye, you might say, well, they've got blobs, and some of these are driven by, there are 3 universities in Cardiff now. We could imagine that kind of thing, couldn't we, driving this, or Leeds, got a lot of rugby union teams in Leeds, a lot going on there. Okay, this is something that we don't have to fight about today. So this is called splitting a city up into modules, and almost, if you've got 3 network scientists, they've got 9 methods to do this. So let's just choose our favourite method, whatever it is. So here I've taken the sainted city of Bristol, wonderful place, yeah, Bristol, love Bristol. And what I've done, I've split it up by, in this case it's by modularity into probably 70 odd cities. I can't remember how many we've got, it doesn't matter. Actually, this is modularity, which gets optimized. This is something else, this thicker line. You can see that most of the work's done by the time we've got round to about here. And then we're forced to moronically go on and on. We must be fitting noise at this point, right? Right. So, I always advise people, to set some sort of stopping rule, which, where you've got something which would be robust to noise, and you could check that if you wanted to. That wouldn't be such a bad thing, would it? So here we go. Comparing different cities is then very easy. If you want to know the details, read the paper. But you take a city, say Leeds, you decompose it however you like into its sub-communities, and then you put all those in a bag. And then you draw out, with repetition, communities. And you keep going until you've made something the size of Bristol, and then you can join it up a little bit if you fancy that. So then you've made something the size of Bristol out of all the components of Leeds. And you do that 1 billion times. That's a very honourable moment, because the computer's doing our work for us. And then we can calculate any performance measure we like over the ensemble of Bristol-sized cities made of Leeds components. And we can also calculate it based on true Bristol. And we can decide whether Bristol sits in the envelope of Leeds-based Bristols, if you like. I should have chosen something else other than Bristol, I feel, but there we go. Okay, so that's what we're doing. And then if it falls inside the envelope, you say, well, that's quite good. If we did something in Leeds, it really looks very similar to Bristol. Of course, we can do it the other way as well. We could, you know, but if it falls outside the envelope, you need to say, well, you know, whatever we did in Bristol, that won't work in Leeds, because Leeds is definitely different. There are fundamental things in Leeds that cannot be replicated by knowledge of Bristol. So beware town planners or councils or about to spend large amounts of money. What we'd really like to do is to put all the cities into some sort of equivalence class, wouldn't we? So that, you know, you cities can look at each other and look enviously at the other cities, but they're not for you. You're in there. And to give a sort of comparison set for cities, even though they're very different sizes. And of course, we want to do this about as far as 100. That takes us down to Guildford as the last one. So University of Surrey just sleeping in there. Great stuff. This is what the sort of stuff looks like. So let me take an example of Bristol here. So here's Bristol, and I'm constructing cities. Bristol itself is bang on. I'm constructing cities, and Leeds falls well outside the Bristol envelope. The green shows the Bristol envelope. So really, actually, there are at least 2 equivalence classes in this data. And we tried to have a little look at that graph and to speak about it. Okay, I've just got a couple of minutes left. I just want to talk about a new topic for us. So whenever we get into an application, in this case, it's urban analytics and cities, we end up talking about approximations because we know we haven't got all the data. We know the data's got false positives and false negatives in. We might want to make calculations that are very expensive and things like that. So a lot of our work really has been about looking at approximations of what, you know, if I know what I want to calculate with the real data, can I approximate that with an easier network to make the calculation easier whilst minimizing the error I'm making? So a lot of this has gone on the quiet, mean field theory, a lot of the stuff we do when we talk about dynamics of networks, where we're really looking at stochastic Markov chains, increasing the measurements of centrality, really like that. If you really knew what you wanted to calculate, you could probably simplify the city and have a, you know, this has gone on for years in applied maths. It's called asymptotic analysis. We form the differential equation up, and then we split it up into problems we can solve, and then glue them back together again. Right? And network analysis has got to the point where it really needs that next step. You know, a group of us in the UK ought to get together and show some leadership before they do it in California. So what with all of this? So it's clear that all cities are not the same, and that clearly impacts on policy, which is a big outball for us. How do cities change over a year? When are they disconnected? Got this great project in Oxford where they look at the sliding doors, the different communities that move through the same spaces. You know, if you take the university out, we're a sort of market town with low educational achievement. You know, terrible things going on up the Cowley Road. You know, there's a lot of problems in Oxford, and we're sliding past different communities. We're occupying the same space. And so I really wanted to get to things like that. I love the idea of having safe spaces for people to walk home at night. You know, as soon as we get real smart cities, that's what they're going to do for us. They're going to look after the citizen. Not the town planners, not the people in Civic Hall, benefits to the citizen, direct benefits to the citizen.
You really haven't ever acted with Oxford City Council, have you?
Well, I have actually. Yeah, I have. And I mean, you know, they're going very slow on some of this stuff because they haven't got any money. That's the bottom line of it. All right, smart city projects are almost always about show and tell devices. And actually there's two-way dividend here. I think we have to observe and drive new analytics from observing cities. And that really does mean humbly observing cities. But then we have to deploy those analytics and think of ways they're going to make a social change. I think a lot of our analytics just gives us a warm tummy feeling, you know, great, we've written the paper in the Royal Society, you know. Actually, we really want to get some impact going out of this, and that's what the ATI wants too. GCRF, Global Challenge Research Fund, the UN Strategic Development Goals, this can't happen without urban analytics and urban environments because so many people are gravitating to urban environments and to cities. So it's a big area in this, and I think that data science in particular, our sort of mathematical science, has to take its place in that. And the universities and the ATI need to become aligned with these sorts of projects, multidisciplinary expertise, and we need to build people who are early career scientists now into authorities in 10 years and 15 years' time. So thanks very much.
So just to say, we're going to take questions for 5 minutes, and Pete's going to do a bit of a wrap-up, and then there's going to be wine and nibbles in the kitchen area. So, but first for questions.
I mean, talking about this in terms of interventions, not just measuring the interventions, that does mean, if we're looking into big picture stuff, that we're going to have political data science, aren't we? I mean, I was somewhat caustic about Oxford Council, but we now have tools for people who want to take action with.
Yeah.
So we actually do we actually need to actually breed people who will do proper experiments and proper maths to deliver this?
Well, two sides to that. I mean, clearly, the data is going to be out there, and the more we get monitored and coded up, the more there's going to be. I mean, this does all belong to the citizen in some way, and so obviously there's some ethical issues around some of the things I talked rather flippantly about, but nevertheless, they do have to be faced. And I think that, within reason, with reasonable access, I think we should aim for that. I don't think we can carry on doing this just in universities or just in colleges.
Did you always just use the Twitter data set? And if so, did you cater for sampling bias of the people who would use Twitter?
No, this only represented the self-appointed people using Twitter.
Okay.
Right?
And
the thing we were trying to get over here was we're faced with labelled graphs, labelled by each city, which did differ on orders of magnitude. And there didn't seem to be any off-the-shelf ways to really compare things differing by orders of magnitude. So this is a nice one because it would allow you to, where Q is any measure that you can calculate. So it was limited to this, and this is what we've made available. But clearly we could have gone with a number of other things.
it was intentional. It was intentional. The difference in the sampling of the people who would use Twitter in the coming up with your maths.
Yeah, so a lot of my work goes to the advertising industry. So Des and I do a lot with digital advertisers. And actually, I know that at the research councils, if you apply for money off the research council, they say, well, it doesn't represent everybody, therefore you can't use this. But the advertisers don't care, you see. They say, well, it's that 18 to 25-year-old group that we can't get to, you know, but they're all on Twitter. So in a funny way, it's exactly where you want to go if you're working in digital media and advertising. But if you want to say something outside of that social, we're saying nothing here because they're clearly not represented at all.
Thank you.
Could you do it for countries?
Sorry?
Could you do it for countries?
Well, yeah, we can. I mean, so we have thought about that in a number of applications. Getting the data is expensive now, so you've really got to have a good reason to pull all this, because we kind of need every tweet that's geo-referenced, and that's expensive. And of course, Twitter aren't exactly making loads of money, you may have noticed. So I think they need to be a bit more friendly to those of us who might put a bit of innovation at the data exploitation end. And those are ongoing conversations. But yeah, I mean, there's a possibility there. There are also sort of security applications of this, which are also, we can see everything if we care to go and get the data. It's not trivial to get the data and clean it up, actually. So we couldn't do that in a maths department. Who would get a data set and clean it up? I mean, so you really, we really did require some professional expertise to sort the data set out before we could deal with it. But so that made the data expensive, I would say.
This is sort of half a question and half a comment, right. Is that it just seems to me the safe spaces thing now has come up twice. So what it seems to me is that, let's say that we make safe paths. Actually, if we do that passively, then we're going to deepen divisions because we're actually going to render some bits of the urban landscape more desolate and abandoned, etc. So it seems to me, ethically, we really don't have a choice if we're progressives, is that we've got to do both, collect the data and think about intervention, because otherwise it's asymmetric. It's going to worsen.
Well, I like that, but the counter argument we learned from Oxford is that we're all, there are these different communities moving past each other, and they're not connected at all. And I mean, we sort of wondered at time of year when all the kids are in school, at least everybody goes and stands in the playground together, right? But when the kids are out of school, arguably in the summers, maybe there is greater division in cities.
There are also warm nights and beer. So, you know, but I mean, yeah, that does need thinking about. But what we'd really like is to be in the position where we could have some intervention, and we could use this sort of thing to just passively monitor whether, in fact, there was greater integration or less integration. I think that would be a really good way to go. And then we'd be right back to how do you compare one data set with another? What's changed, kind of thing. These sorts of questions. Which could be answered by other things too, you know, persistent homology, data clouds, or there's lots of other things that you could do. This is only one game in town, and probably not the best.
Hello. Just flipping it around, if you were the managing director of Twitter UK Limited, and you see your graph about the 10 cities, what would your strategy be regarding your product?
Okay, so I'll give you a quick example. If we knew where everybody was, I suppose we've got the network of London in front of us, and we knew where everybody was who used Colgate toothpaste, they'd all put their hands up. Actually, that's more or less a random pick. We all use toothpaste. We never talk about it. We don't ask each other which brands we buy. It's the same with asthma. If you say, who's got asthma? You put their hands up. That's a random sample by Vertex of that. So actually, if you want to talk to the asthma sufferers or the Colgate toothpaste users, you're broadcasting. You've got to talk to everybody. Get on the back of a bus, get offline, right? If you go for Jaguar cars or other kinds of high-value things that their owners like to talk about, they also go to the same golf clubs. It doesn't matter why they're all bunched up and things like that. But actually, there's obviously a whole load of knock-on, a lot of buzz in the trade and that kind of thing. So one of the things we could do is rank order all the brands in the country by the disproportionateness of their buzz. I mean, that would be good, because when advertising companies ran campaigns, they'd say, we've increased the size of your footprint and we've actually increased its sort of connectivity or density or something. You've gone from 38 to 31, right? And the owners would say, what does that mean? They go, great, we've gone from 38 to 31. You know, it would become de facto. They need to make sort of de facto measures that would be performance measures for advertising campaigns. That's what I'd do. And they could do that. Dead easy. Let's wrap up now, because there's only me here between you and a glass of wine, and I'm feeling thirsty myself. Look, everybody, it's been lovely having everybody come along, but I just want to spend a few minutes where we go around and ask you guys, what's your feeling about all this? At the ATI, we want to have a thread which is around urban analytics. Clearly, we're aligned with some of the government things I talked about there, GCRF, spending large amounts of money working here and overseas. Clearly, it's of interest to some industries and not of interest to other. You know, how does this strike you really as a theme for research and something that you'd be involved in or that you are involved with? Let's have a few comments from the floor. Don't be shy. Yes, please.
I'm just wondering how much of this research is informing policy? Because I came here, like I've heard about in the realm of smart cities, pollution modeling or self-driving cars, things that will.
Well, not enough of it's informing policy. That's my view. Particularly, we've got this thing where I'm going to speak against the air pollution thing for a minute. Right, so air pollution, we can monitor if we've got the sensors in there. It's really just a question of having all the sensors there and things like that. And then what do we do about it? Well, you say, well, we've now increased, where I live in Henley-on-Thames, we've now increased the quality of the air by holding cars back up Remenham Hill. How do I feel about that when I'm trying to get home to watch Manchester United? I don't want it. Right, so unfortunately the civic goals are in direct conflict often with the citizens' goals, and that doesn't, you know, always shine through. But at least if they're going to have fact-based policy, then they're going to have proper data and proper analysis of it. That's my view, really. So we can have the argument about citizen or civic goals. We can have, but I mean, fundamentally, more of us who are trained as data scientists within Silo have to develop some skills to go and influence policy and things like that. And I know that at the Alan Turing Institute, we're going to have a sort of policy unit where we can get some of that training and get some of that, because otherwise we're going to be leading it to the MBAs and others who are just turning up and saying whatever they like on the basis of, you know, a good degree. How shocking would that be? So I think we do need to get data scientists into that, but what we mustn't do is just constantly spout data science. We've got to meet them halfway and understand the nature of the policy questions. And that's quite difficult, but I think it's something that we can all do as data scientists.
Speaking of engagement, I'm Vice Chairman of the Conservative Technology Forum, and what we observe, just from being sort of, I'm both sides of the fence, but when I stand the other side of the fence, is it's basically people who are trying to sell us stuff who actually turn up. Twitter, we have Twitter are members, or almost everyone that's a corporate member of our group, or actually a member of our group, is a firm you will have heard of.
Yeah.
And what we don't have is academic level. People just coming and telling us interesting stuff we can try and shove in a report.
Yeah.
And we do get the impression, speaking quite brutally, people don't want to speak to us as much as we want to listen to them. We've had to more or less mug people to try and get engagement. And I think part of that is a slight fear that what they're saying won't make it into policy, because A, it's true, because it doesn't always make it into policy, but B, if you don't try, it really doesn't happen. And people do need to have a go, and if it doesn't work, it doesn't work.
Yeah. No, this is right, but I mean, there's a pipeline problem in that for too long we've sort of siloed our disciplines, and success in mathematics looks like doing more mathematics, and there's a career there, a very good career, I think, for people who want to be commentators, who want to be policy advisors, who want to be journalists, actually, that have this deep data science background. I think there is a need for more rational umpires. It's dangerous because you might feel as a career you might get pulled into one argument or another, and but I think there is a need for the sort of rational umpire in all this, particularly because a lot of the results that are going to come out are really going to be uncheckable by human minds. I mean, that's an ethical issue we haven't really got time for today, but you know what I mean. I mean, it's not as if we can go and get all the data that Google's got and just check what they're telling us. Is it? Because even if they give us the data, it takes us a month of Sundays to unwrap it. So I think that once data and alleged insights from data, and that's an ethical thing. So one of the things that I've been thinking about this year quite a lot is that the importance of placing ethics within data science education and understanding the role of whistleblowing, that kind of thing. Because if you're not if you're in a company, then sometimes bad things happen in companies for good reasons, Frankenstein type reasons, and someone needs to tell someone on the board in words that they will understand, because it's shareholder value that will be lost there. They won't just get hit over the wrist with the ethics committee. They lose shareholder value. Ask Volkswagen.
It seems to me that there's a lot of data in online petitions and so on.
Yeah. Well, there's quite a lot of analysis of that. I do know at the Oxford Internet Institute, they've written papers on the whole petitioning process in terms of what it's reflecting, the moods that it's reflecting. And Cameron was always one step behind public, wasn't he? Never could quite be there at the right moment. And now we live in a 24/7 kind of world where over a weekend 1 million people can sign up to something. That kind of changes things for politics and policy wonks, really.
I see why you're shaking your head, because obviously those petition people are hardly a random sample, are they?
I know.
But
I mean, they have that ability.
But I think it's not just a question of what they sign up to, it's a question of word clouds of what they put in their comments.
More people in the first week signed up for Spandau Ballet's Gold becoming the new national anthem than Trump not coming to England.
Well, there we have it. There we have it, ladies and gentlemen. Okay, look, let me just finish it off there, look, because I want to continue this over drinks, but we do all need a drink now. We've been very good. We've sat and listened. I want to say thank you to the organisers here, and Chanuki, and thank you to the Royal Society for putting this on. When you're on your way home, the good news is that we've got a lot of people in this room that want to work in this area. Look, we've got to get this community going. and there are going to be opportunities. We mentioned some of them for funding both internally and externally, in the country and out of the country. And so this is kind of an exciting area of growth for us. But we need to be imaginative and think about experiments which are going to have an impact, which are going to get us into the room when big stuff's decided. Okay, and that's the challenge for us. We've got to get out of our comfort zone and maybe meet some of the policy people halfway. Thanks very much for organising this.